All right, today's speaker is Yangchen Pan. He's going to tell us about an implicit function learning approach for parametric modal regression.
Okay, let's get started. So I'm going to talk about an implicit function learning approach for parametric modal regression. I would like to mention that this is a co-work with Esam, Martha, Amii, and Masood. First, I want to talk about what modal regression is and why we care about modal regression. The purpose of modal regression is to predict the set of conditional modes given a testing point, in contrast to the well-known like L2 regression, which try to predict conditional mean. Assume that P of xy is a data generating distribution. By doing modal regression, we actually try to predict a multi-valued function, m of x here. M of x is the set of conditional modes given point x. It is the local maximum with respect to y. So the first order derivative is equal to 0, and the second order derivative is less than 0. The conditional mean is defined as the expected y value given x. This can be done by minimizing mean squared error. Let's see a concrete example. The left-hand side shows a data set, a noise-contaminated circle data set. The circle is centered around the origin with unit radius. The right-hand side shows the conditional probability distribution y given x equal to 0. So we can see that when x is equal to 0, the set of conditional modes is 1 and -1, and the conditional mean is 0. The conditional mean can be found by simply minimizing mean square error. And you can see that by predicting y equal to 0, given x is equal to 0 is meaningless because the density of y equal to 0, given x is equal to 0 is very low. So this is unlikely to help decision making. This example actually motivates modal regression. Predicting conditional mean can be meaningless when the conditional distribution y given x is highly skewed or multimodal. In contrast, modal regression is robust to various data distributions. Many existing work in modal regression algorithms are non-parametric or semi-parametric. That means they are difficult to scale to large data set or high-dimensional data set. So our purpose is to design the parametric modal regression method, which is scalable to large data. And the second goal is we want our algorithm to predict the set of all conditional modes. Many existing work can only predict the highest likelihood mode, and they assume that such mode is unique. Our key idea is to learn the implicit function f of xy equal to 0.
Yangchen, so interrupt for just 1 second. Rich, I don't think Yangchen can see us, so you could just pipe up.
Okay, good. Oh, so I have a question, Yangchen. That was great. You told us what was wrong with conditional means, but you didn't. I didn't get what a conditional mode is.
Oh, so let's go back to this example. Yeah. So when we can consider the circle data set as a bimodal distribution given an x point, right? So let's say given x is equal to 0, the corresponding target is sampled from a bimodal distribution.
Yeah.
Right. The conditional mode is a condition on x is equal to 0. The conditional mode is positive 1 and negative 1.
The mode is 2 numbers.
There are two modes. You can see on the right-hand side because it is a bimodal distribution. So there are 2 modes.
I guess more generally it's a set.
More generally, it's what is a mode? Can you say what? I mean, you're saying that in this example, the mode would be the two tops of the 2 bumps. But is there a general? What do you mean by I could see that would be a good thing. But what if there were 3 bumps or 4 bumps? What is a mode?
The mode is the point. It is the local maximum with respect to y of the conditional probability distribution. All of the local the set of local maximum given an x value.
The set of local.
Those are the modes.
You can look at the m of x, this function. So it is given an x value. It is the set of corresponding y all of the local maximums. So the local maximum are those points with first order derivative equal to 0 and the second order derivative less than 0. So this is a set.
Thank you.
So our key idea is to learn an implicit function in the form of f of xy equal to 0. So you can see that this function takes both the input feature x and the target variable y as input to describe the xy relationship. So we can consider the circle example again. So we know that the circle can be expressed as an implicit function x squared plus y squared minus 1 equal to 0. So our idea is to try to approximate such an implicit function. So let's take a look at the implicit function learning objective. Given the point x, y, there are two parts in the loss function. The first part is f subscript theta, f parameterized by theta of xy squared. And the second part is we try to push the partial derivative of f with respect to y equal to -1. For comparison purpose, I also put the regular L2 regression objective here. So you can see that L2 regression simply minimizes mean squared error. And we parameterize a function g parameterized by theta. And this function only takes x as input. So to an intuitive understanding of our objective is that we can think of fxy as directly parameterizing the error function. That is, for each xy from the training set, we can think of that there exists some function g defined locally around that point, such that f of xy equal to gx minus y. So the first part in the implicit function learning objective is that we try to minimize the error. And the second part is try to make sure that there exists some function g to express y in terms of x, although we do not explicitly learn this g. Here is a probabilistic interpretation of our objective. We can consider the random variable. The training set xy is sampled from some mixed Gaussian distribution. A training sample, a realized random variable xy, can be thought of as generated by first sampling x and then sampling an index j denoting the jth component in the mixture of Gaussian. Then we sample the target y from the corresponding Gaussian distribution. So recall that the regular L2 regression assumes y given x is Gaussian, but we directly assume the error g of x minus y is Gaussian with 0 mean and some constant variance for any j, for any component. And the important thing is that our assumption is weaker than the regular L2 regression. We can recall the circle example again. On the circle example, given the y given x is a bimodal distribution. That's why if we run L2 regression, minimizing the mean squared error, it doesn't work. It doesn't give meaningful prediction because it violates the probabilistic assumption that the conditional distribution should be Gaussian. But the error is still Gaussian with 0 mean and standard deviation. So our assumption still holds in this case. So the next problem is that how to do prediction given a testing point x star. We propose two ways to do prediction. The first way is to predict those modes with highest likelihood. That is, given testing point x star, we find all of the corresponding y values to minimize the loss function. The second way to do prediction is to predict all of the conditional modes. That is to find all of the local minimum of the loss function with respect to y. Here is an example. Assume that after training, we get a loss function when x is equal to 0.5. The loss function is shown in the red curve. And there are two locals. So when we try to predict all conditional modes, it will return A and B, the 2 points. When we try to predict the mode with highest likelihood, it would only return U point A, because that point has a minimum loss. There is a sensible problem of our method. So how can we avoid incorrect y values, those incorrect modes which achieve the same loss as a true mode? We propose to use a regularization strategy motivated by theorem 1 here. The theorem 1 states that if a function f has a bounded second-order derivative magnitude, then assume that point A has a function value epsilon and a slope k. Then there does not another point within a certain distance to A such that the point B has the same function value as A and the same slope. So the interpretation is this. We can consider that given the testing point x star, we can consider the f of y in the theorem 1 is the function f subscript theta, given that x equal to x star. So we consider y as the independent variable. And then we can consider the point A in the theorem 1 as a true mode, and the slope k equal to -1. So we expect that the point A achieve the minimum loss. This theorem then says that there does not exist another point which is close to A, and that point has the same function value and the same slope k. This means that there does not exist another point close to A which can be a spurious mode. So this theorem motivates a regularization strategy because the distance of the spurious mode to the true mode has a lower bound on the distance, which the distance is inversely proportional to the magnitude of the second order derivative. As a result, we can try to punish the magnitude of the second order derivative. This gives the regularized implicit function learning objective. Here is an empirical demonstration. When x equal to 0.5, the highest likely, let me first introduce data set. The data set is still a circle data set as shown in figure A. And the difference is that on this data set, when x is less than 0, it has a high likelihood mode on the positive part. So you can see there are more points for in the positive part when x is less than 0. When x is greater than 0, it has a high likelihood mode on the negative part. So you can see there are more points for on the negative part. So we visualize the loss after training with and without regularization when x equal to 0.5. So when x is equal to 0.5, the high likelihood mode should be negative. And you can see that without using the regularization, the loss function cannot help us identify high and low likelihood. The two modes seem to have the same loss. So when we try to predict the modes with highest likelihood mode, it will give us both the positive and negative one. But with regularization, we can see clearly that the negative mode has a smaller loss, so we will get this prediction. I further visualize the prediction on this data set. I visualize the predictions of evenly spaced points from -1 to 1. The left-hand side figure shows the prediction of highest likelihood mode without corresponding to the algorithm without using regularization. We can see that when x is greater than 0, we get incorrect predictions in the sense that it also return us some low likelihood mode. But with the regularization, as shown in the middle figure, we see that when x is greater than 0, we get all points, all correct predictions on the negative part. And when x is less than 0, we get correct predictions on the positive part. So this shows the utility of the regularization. And the right-hand side figure shows the prediction of all conditional modes. And the visualization looks similar with and without regularization. So I just put one figure here. So there's one thing worth mentioning is that we do not see very incorrect predictions in the sense that we do not see any points fall in the middle of the curve of the circle. We only, without the regularization, we can see incorrect predictions in the sense that we cannot identify whether it is high or low likelihood. So this actually interesting because it seems that even without regularization, we do not see a very wrong modes. We do not see such very incorrect spurious modes. And we found that the regularization is not needed in many cases, actually. So we try to find out the reason why this can happen. We show theorem 2 here to explain, to give some intuitive reason for why it is unlikely to see a spurious mode, even without the regularization. The theorem 2 states that let fx be a continuous differentiable function, and let x1, x2 are 2 points with the same function value and the same slope sign. Then there must exist another point between x1 and x2 such that it has the same function value and a different slope sign. So here is an example. The figure shows an example here. x1, x2 has the same function value and the same slope sign. And then we can see that there exists another point x0 in the middle, which has the same function value but a different slope sign. So if we consider x1 as the true mode, x2 as the spurious mode, that means every time we get a spurious mode, it will have such a wave pattern within -1 to 1. That if there are 2 spurious modes, then there will be one more such wave. So it is unlikely for a function to naturally look like that without intentionally training it like so. So this is the intuitive reason for it is unlikely to get spurious mode. So that's all my presentation today. So are there any questions?
I have a simple question.
Yeah.
I want to know what X is, because with regular regression, we're used to X being a vector, but
yeah, in this case,
partway
X is also a vector. X can be a vector or scalar.
I thought you took some derivatives with respect to X in your definition of the problem. So X can be a vector.
Yes.
Wow.
So in my because I use a simple data set, the circle data set example.
Yeah. Yangchen, I did get lost in your talk. I'm trying to, two things. Think what you might do to help guys like me not get lost, and at the same time, I'm trying to figure out what is going on in here. So a mode, I think it would help if you said that a mode is a local maximum.
Yeah.
And or maybe even said it, I don't know. But of course there could be it's a set, okay?
Yeah.
So it would help me if you can explain what it might mean to have a loss function of a set. You have a set of modes, and I have some algorithm that produces a set of modes, and then how can I say if it's good or bad? What kind of a loss function would I have? Or what would I be trying to minimize?
So are you confusing about the implicit learning objective?
I think I am. I mean,
maybe this is a more general question about how do you evaluate any kind of modal regression algorithm? Like if I'm looking at a set and I'm comparing a set that I output, how do I know if I did a good job or not? Not like how do you optimize for this?
So the answer is in general, in all of the existing literature I see, so some people just visualize the predictions, and there are some people just assume because their data set has a unique highest likelihood mode. So they might just use the same evaluation with such as mean square error, something like that, or root mean square error. But in our case, we develop different ways. So one way is to depending on our demand. So if we want to check the highest likelihood mode, then given a set, we might compute the closest distance we might compute the prediction to its closest true mode, and compute the root mean square error based on that prediction to evaluate the algorithm. And in another case, we might also use some metric computing the distance between two sets, such as Hausdorff distance, to evaluate the distance between two sets.
So what I'm hearing is that, you start out with kind of comparing the mean, conditional mean, conditional mode, advantages of each one. So it feels like you should mention this as a sort of a disadvantage of the modal regression, is that there's no clear way to take a data set and say how accurate was the modal regression on the data set. Whereas the mean square error with a normal regression, mean regression, you just take the squared error.
Absolutely.
And we don't have that.
Yeah, it is very frustrating that it's easy to generate. Of course, it's easy to test the algorithms on synthetic data. There you actually know what the modes are. You could just go check, are my two sets the same? But for real data, we had to try to simulate it on real data by like removing a feature, and then for sure you have the spine modal distribution. But again, that's just cheating. So actually, I was going to bring up as a discussion, what can you guys imagine using modal regression? Like it's a real setting in statistics, but sometimes it's hard to understand who would use it because it is so hard to test. How do you know if you did a good job or not? I mean, maybe one way is if you use it for the stock market and you make more money than the guy who's using regression. I don't know, but that's sort of indirect.
Well, just to complete the thought about the presentation, I think it's controversial, or it's not clear how you should evaluate, how you should make a loss for a modal prediction. And so this gap, this sort of theoretical problem, I think maybe motivates your implicit learning objective. It's because you don't have a conventional loss that you have to introduce this additional idea, right? Because I was listening to you, and I was just, there was this additional thing. I said, why are we talking about an implicit learning objective? Why don't we just take the real objective? And I didn't quite realize that it's because there isn't an obvious objective to use that we are developing this new objective and slightly changing the problem. This is really a change in the problem, or a reformulation of the problem of the modal regression. And if you expressed it that way, I might have understood it better. Okay, thanks.
Martha, I just wanted to chime in and say, in terms of real world data, it seems like there are a lot of different patient data populations that might be really interesting here, that are hard to have a single loss function, but where you actually do care about the modes. There's no like average patient that sits in the middle of your donut. We're almost always faced with very diverse populations that have modes in the data that we can't find and might want to regress to. So it seems like there's actually quite a few natural data sets. We might even have a couple of ones that you might want to play with. Yangchen, like that's a real thing that we could chat about later. But it seems like that's a natural fit case, and there are ways that eventually you can get towards the ground truth, even if it's not immediate. You can do retrospective sometimes to see what the modes were post hoc based on more in-depth evaluations. So anyway, it's interesting. That seems like a natural application case.
So another way to understand it is clustering, like you're trying to find the clusters in the, yeah. Well, that would help me in intuition also talk about clustering.
All right. Yeah.
The other way, of course, could be to start off with the actual natural solution to this problem, which is just to learn the density. You could learn probability of y given x, and then if you could always go figure out what the modes are doing that. Although even that's not an obvious solution sometimes, how you go extract the modes from a multimodal density. But anyway, you could try doing something like that. And then say, well, what if you don't want to learn the entire density? Well, maybe you could try to just directly predict what you want, which is the modes.
About something in between modes and clustering, and level set estimation came to mind, right? So that's also one problem that people looked at in the machine learning literature. This is when you have a density, right? Like it's like goes up and down, and then you cut it somewhere, and then you want to get the region where the density is high enough. So that's like a more robust notion of the modes. And then if you're thinking about that, you have these Gaussians with multiple bumps, and then you cut at the right level, then you end up with two clusters, and then you want to kind of capture the mass there. This also goes a little bit, yeah, like it's more global in the sense that, right, so where do you have high density? Like in a way, maybe this is an easier problem because it's just going for the high density regions where you have points anywhere. So but I don't know. Yeah, so this is something that people have studied,
That sounds like the cross entropy method, but you used a different word. What did you just say? You said it sounds like the
level set estimation. It's called. That's just the name of the problem. Estimating level sets.
Level set.
Level set. Okay.
Yeah. The techniques are somewhat similar to what you have here, except that don't need to take derivatives, I guess.
Cool. We should definitely look at that.
Yeah.
Thanks, Trevor.
So yeah, actually the first version of this work, I name it as level set prediction.
So full circle now. Yeah. It's an interesting problem. People, like in outlier detection, whatnot, are wondering about these level sets. One class classification, that was one fashionable name for a while in machine learning that was related to level set estimation.
Right.
Yeah. Cool.
Yep. All right, I'm gonna go.
Okay. Bye.
Thanks, Yangchen.
Yeah, it was a good discussion. Thanks.
Okay.
That was super cool. Thank you.
Thank you. Bye.
All right, let's all thank the speaker.